Here is our example walkthrough for oxygen and water following our examples of hydrogen. So the first thing that we're going to do is figure out our valence electrons. And so we're going to take our oxygen, and we know that it's got 6 valence electrons and that there are 2 of them. So we say 6 plus 6 equals 12. And then what we're going to do is, because again we've only got 2 elements, we're going to place them side by side. And what I like to do, and we'll go through these notes in just a second on your soft yellow note sheet of paper, but what we like to do is we like to fill in those electrons around the outer parts of the atoms first before filling in the middle, because we need to see if we need to make any double or triple bonds. And so we're going to fill in the 6 electrons around both oxygens, and in this case then we're going to count and see if any of the oxygens are happy. And so both of the oxygens only have 6 electrons and they're not happy. So now we've got to figure out what to do to make them happy. So let's reference our Lewis structure notes real quick. So on your soft yellow sheet of paper with all of your chemical bond notes, our drawing Lewis structures. You know a lot of this already because we've talked about it a couple of times with the hydrochloric acid, the HCl, and the hydrogen example. But let's just look here. So the first thing we're going to do is determine the total number of valence electrons, S&P, so again step 1 that we've already been doing. And then we're going to determine the arrangement of the molecule. So far we've only ever had 2 atoms, and so we've just set them side by side. But if we have more than 2 atoms, what happens is that the least electronegative atom goes in the middle. Our only exception to that is that hydrogen will be the least electronegative atom in some compounds, but it cannot go in the middle because it can only hold 2 electrons. So hydrogen will never be our central atom. We also, if we only ever have 2 atoms, will set them side by side to each other. We're going to place lone pairs of electrons around the outside atom first, again except hydrogen, so that each atom is surrounded by 8 electrons. So we're going to then, we've shown that in our example so far, so that's how chlorine got those. We shared with the hydrogen, and then we put the other 6 electrons around chlorine. We're then going to put electrons around the central atom to be equal to 8 electrons. If the central atom has fewer than 8 electrons, so our oxygen for example, we're going to move over lone pairs to form double or triple bonds. In general, a double or triple bond forms between carbon, nitrogen, oxygen, or sulfur, so kind of keep your eye out for those. We've talked about this already, but we're always going to change paired electrons from bonds to a dash, so instead of 2 dots we would like a dash if you're showing that those electrons are shared between atoms. To determine if the bond is polar or nonpolar, and to put arrows is going to be the next step, and remember you're going to put your arrow towards the more electronegative atom. And then our last thing is going to be to determine molecular geometry. So again, we've talked about all of these steps. I just want you to see that this is where I'm getting those steps from. So if you're not sure on the steps, you can always reference back to your Lewis structure notes, and we'll again get way more practice with this together, both with simple and complex compounds. And so our molecular geometry or shape again is just using the A, B, and E from the Vesper table and then telling us if our molecule is the same or different, so if it's polar or nonpolar. Alright, so now we're back to our oxygen. So now essentially what we need to do is flip pairs of electrons to make everything happy. At this point in the video, I'm going to do a lot of erasing, so I'm going to do a lot of writing and a lot of erasing. You don't necessarily need to erase things if you feel like you just would like to redraw it so you can see the steps. I'm just going to run out of room. So we're going to take one of the pairs of electrons and we're going to share it in the middle. And we're going to check to see if the electrons are happy. So this atom is happy, this atom is not happy. This one has 8 around it, but this one still only has 6 around it. So we need to flip another pair of electrons. It doesn't make sense to flip from this atom because that would still only give 6 electrons to this oxygen. So what we need to do is then flip from the left-handed oxygen. We're going to check again to see, and both atoms are happy. So there we go. So we have a double bond with oxygen. I'm going to redraw it just so things are out of the way. So this is what it's going to look like. So one of the things that we need to learn here is that when we are dealing with electrons, the Vesper theory tells us that electrons are going to arrange themselves around an atom so that they are as far away as possible. So we need to adjust where these electrons are because right now they are not as far away as possible from each other. So we're going to redraw them and move them at an angle around the electrons. We're going to take the dots and move them to dashes. And then we are going to show, you don't need to draw on the red lines, but I'm just trying to show that that's the most space between the electrons, and this is the correct Lewis structure for oxygen. If you keep your Lewis structure like that, that is considered the incorrect Lewis structure, because first of all you need dashes instead of dots, and then you also need to make sure that you're applying the Vesper theory and showing those electrons moving around. Alright, so then the next thing that we're going to do is figure out our shape. So here I've got two atoms that are the same. So I've got A and A. I know that that's A2, and if I look on my molecular geometry Vesper table, it's going to tell me that that's linear. The next thing I'm going to do is figure out my bond type. So I go to my electronegativity periodic table, and I look at oxygen, and I see that oxygen is 3.5 minus 3.5, which equals 0, and I know that that's a non-polar covalent bond. So hopefully you're looking for oxygen as well, and you're looking at the linear sheet so that you see that that is indeed linear. And then the arrows, those are sharing equally, so I'm going to make sure that I draw double arrows over here, so arrows for both bonds, showing that those are shared equally. And then lastly, it's a non-polar molecule, because this looks the same on all the sides. So with oxygen, again, we're going to have a double bond, and it's a linear molecule, and it's going to look the same on all the sides. Alright, now let's look at our water example. So first thing we got to do is figure out our valence electrons. So our valence electrons, I know I've got hydrogen is 1 plus 1 plus 6, so I have 8 total valence electrons. The next thing I want to do is draw my Lewis structure. So based on my rules, I'm going to put the least electronegative atom in the middle. But our exception is hydrogen. So hydrogen is the least electronegative atom in this case, but hydrogen can only have one pair of electrons, so oxygen will need to go in the middle in this example. So I'm going to line it up where I just have oxygen and two hydrogens next to it. Sometimes when we're doing Lewis structures, we're going to need to redraw things based on what the Vesper table tells us. And so that's why I'm just starting this with the hydrogens on either side of the oxygen. So the first thing that we're going to do is we're going to take two of the electrons and share them immediately with hydrogen and oxygen, because hydrogen, normally we fill around the outside of all of the atoms first, but hydrogen can only have 2 electrons, so we automatically share those 2 electrons with the central atom first. Then I'm going to fill in the rest of the electrons around the central atom, which will be 2 on top of the oxygen and 2 electrons below the oxygen, so 1 electron pair. Alright, then we're going to count to make sure, are these happy? So hydrogen's happy with 2 and oxygen is happy with 8, so we're good on filling in our electrons. Now we're going to look at our Vesper shape. So we're going to go to our molecular geometry sheet and identify if your central atom has lone pairs on it. We definitely need to go to the Vesper table, because most likely you will need to redraw the Lewis structure to be the correct Lewis structure. So those are our lone pairs on our central atom as a reminder, and if we look at our Vesper table, we've got 2 atoms bonded to the central atom, and we've got 2 lone pairs on the central atom. Well, first of all, guys, water is our example here, so this is what our final Lewis structure for water needs to look like, but we also need to make sure that we're aware whenever we have lone pairs on our central atom, we're either going to have a pyramidal or bent Lewis structure. So we need to make sure that we're drawing that accordingly. And so, again, our four electron groups, 4 pairs or 4 shared things around the atom, and we have 2 and 2, and our type of molecule will be AB2E2. So if we go back to our sheet here, I can look at labeling A, B, B, those are my atoms bonded to the central atom, and then E, E, those are my lone pairs. So I would say AB2E2, and you can say bent. So again, at this point, if you write that it is a bent molecule and leave it in a linear shape, it is going to be incorrect. I cannot stress that enough. You need to make sure that you're showing that in a Lewis structure that you have a bent molecule, and you need to redraw it looking right like that, and it gives you that guidance on the Vesper table sheet. So then what we're going to do is figure out our our bond polarity. We subtract those two and we figure out that we have a polar covalent bond. We're going to draw in our arrows, so electrons are shared unequally. The electrons will hang out more around the oxygen molecule because it is more electronegative. We're going to redraw it and have it look right like that. And those two symbols right there are simply showing a relative charge on the atom. So on the molecule, we have a relative charge. Now, if our molecule is polar or nonpolar is where it's really important that we draw our Lewis structure the right way. Because if we draw our Lewis structure showing that it's bent, we know that it's a polar molecule because this side does not look like this side. But if we do not fix our Lewis structure, you are going to tell me that it's a linear molecule, and that will be incorrect. So please make sure that if you draw that if you tell me that it is a bent molecule, you need to draw it like a bent molecule. If it has lone pairs on the central atom, it will be a polar molecule. Thank you so much for watching all 3 of these videos and coming prepared for class. You will have maximum amount of time now to work on these practice problems together in class with us because you've spent so much time preparing. Thank you.